According to the National Electrical Code, all electrical systems must be properly grounded to ensure safety and prevent electrical hazards. When working with both 277 volts and 120 volt systems, specific grounding requirements must be met. Firstly, let's discuss the grounding conductor for the 277 volt system. The conduit used for the 277 volt system must include a separate grounding conductor. This grounding conductor must be connected to the neutral conductor in the 277 volts J-box. The 277 volts grounding conductor must be extended into the panel and connected to the grounding busbar. Secondly, the 120 volt system also requires a separate grounding conductor. The grounding conductor for the 120 volt system can be extended from the 277 volts J-box to the 120 volts panel. Alternatively, the 120 volts grounding conductor can be connected to a grounding rod or other suitable grounding electrode. Thirdly, in addition to the grounding conductors for the 277 volts and 120 volt systems, an additional grounding conductor can be installed to provide redundant grounding. This additional grounding conductor can be connected to the grounding busbar in the panel and extended outside to a grounding rod. To ensure proper grounding, install both the grounding conductor for the 277 volt system and a grounding conductor for the 120 volt system. The 277 volts grounding conductor can be extended to the 120 volts panel, or a separate grounding rod can be installed for the 120 volts system. An additional grounding conductor can be installed for redundancy, but it is not required by code. When installing grounding conductors, several factors must be considered to ensure effective grounding and compliance with electrical codes. This includes the size of the grounding conductor. The size of the grounding conductor is determined by the size of the overcurrent protection device in the circuit. The NEC Table 250.122 provides guidance on the minimum size of grounding conductors based on the rating of the overcurrent device. Using the correct size grounding conductor is essential for providing a low impedance path for fault current to return to the source, facilitating the operation of the overcurrent device and clearing the fault. The material of the grounding conductor is also a factor. Grounding conductors are typically made of copper or aluminum. Copper is the preferred material due to its excellent conductivity and resistance to corrosion. Aluminum grounding conductors are permitted, but they must be sized larger than copper conductors to achieve the same level of conductivity. The type of grounding electrode used also matters. A grounding electrode is a conductive object that is buried in the earth and connected to the grounding system. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. The NEC specifies the requirements for grounding electrodes in section 250.52. Ground rods must be at least 8 feet long and driven into the earth so that at least 8 feet is in contact with the soil. Ground plates must have a surface area of at least 2 square feet and be buried below the permanent moisture level. Metal underground water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. The location of the grounding electrode is also very important. The grounding electrode should be located as close as practicable to the electrical service entrance. This minimizes the length of the grounding electrode conductor and reduces the impedance of the grounding path. The grounding electrode should also be located in an area where the soil is consistently moist to ensure good electrical contact with the earth. The installation of the grounding electrode conductor is essential. The grounding electrode conductor connects the grounding electrode to the grounding busbar in the electrical panel. The grounding electrode conductor must be sized according to NEC Table 250.66. The grounding electrode conductor must be securely connected to both the grounding electrode and the grounding busbar. The connections must be made using approved connectors and methods. The bonding of metallic components is also very important. All metallic components that are likely to become energized must be bonded together to create a low impedance path for fault current. This includes metal conduits, metal enclosures, metal water pipes, and metal gas pipes. Bonding is typically accomplished by connecting the metallic components to the grounding bus by using bonding jumpers. The inspection and testing of the grounding system must be done regularly. Once the grounding system is installed, it should be inspected and tested to verify that it meets the requirements of the NEC. The grounding electrode resistance should be measured to ensure that it is low enough to provide effective grounding. The connections should be inspected to ensure that they are tight and secure. The grounding system should be periodically inspected and tested to ensure that it continues to function properly. Specific requirements can be found in NEC Articles 250.50, 250.52, 250.53, 250.56, and 250.68. Maintaining a low impedance ground is critical for electrical safety. A low impedance ground provides a path for fault current to flow back to the source, allowing the overcurrent device to quickly trip and de-energize the circuit. A high impedance ground can limit the flow of fault current, which can prevent the overcurrent device from tripping and create a shock hazard. The impedance of the grounding path can be affected by several factors, including the size and material of the grounding conductors, the type and location of the grounding electrode, and the quality of the connections. To minimize the impedance of the grounding path, it is important to use appropriately sized grounding conductors, install grounding electrodes in areas with moist soil, and make sure that all connections are tight and secure. The purpose of equipotential bonding is to minimize voltage differences. Equipotential bonding is the practice of connecting all metallic components in an area to create an electrically common surface. This minimizes voltage differences between the metallic components and reduces the risk of electric shock. Equipotential bonding is particularly important in areas where people are likely to come into contact with metallic objects, such as bathrooms, kitchens, and swimming pools. The size and type of grounding and bonding conductors are critical. The size and type of grounding and bonding conductors must comply with the requirements of the NEC. The size of the grounding conductor is determined by the size of the overcurrent protection device in the circuit. The size of the bonding conductor is determined by the size of the largest ungrounded conductor in the circuit. Grounding and bonding conductors must be made of copper or aluminum. Copper is the preferred material due to its excellent conductivity and resistance to corrosion. The NEC has requirements for identifying grounding and grounded conductors. Grounding and grounded conductors must be properly identified to ensure that they are not confused with ungrounded conductors. Grounding conductors are typically identified by their green color or by green insulation with one or more yellow stripes. Grounded conductors are typically identified by their white or gray color. Ungrounded conductors are typically identified by their black, red, or blue color. In summary, proper grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing the overcurrent device to quickly trip and energize the circuit. Bonding minimizes voltage differences between metallic components and reduces the risk of electric shock. It is important to comply with the requirements of the NEC when installing and maintaining grounding and bonding systems. This involves using appropriately sized grounding and bonding conductors, installing grounding electrodes in areas with moist soil, making sure that all connections are tight and secure, and properly identifying grounding and grounded conductors. Understanding the specific requirements for 277 volts and 120 volt systems is critical for ensuring a safe electrical installation. Remember to always consult the latest edition of the NEC and local electrical codes for specific requirements in your area. Electrical work should only be performed by qualified professionals to avoid potential hazards and ensure compliance with all applicable regulations.